A star has a radius of 3.5 times 10 to the 8th meters and a temperature. This is a smaller star than our sun, right? 4,280 kelvins. What is the power output of the star? Okay. So the power output is going to be emissivity. So we'll assume that the emissivity is 1.00, right? I'm using emissivity sigma area, the Stefan-Boltzmann, right? So our sigma is 5.67. That's the Stefan-Boltzmann constant. Okay, area is going to be 4 pi times 3.5 times 10 to the 8th, and then don't forget to square that. Okay, so let's see, we've got emissivity, and we're just assuming it's a black body radiator. Perfect one, right? And then there's our, okay, we got our area, and then we need our temperature, right? So 4280 kelvins, and that's to the 4th. Okay, so let's go 1 times 5.67 times 10 to the minus 8th times 4 times pi times 3.5 times 10 to the 8th, but don't forget to square that, times 4280 raised to the 4th power. Okay. Okay, so this thing's no slouch. Okay, it's not the sun. The sun was like 3.85 times 10 to the 26th, right? This star is no slouch, though. This is putting out 2.928896 times 10 to the 25th watts. So it's a, you know, nothing not to be proud of there. Okay, and now we're going to figure out what is the intensity at the distance we are from it, right? Well, remember that intensity is power divided by area, and we just figured out the power, right? And if we are 1.3 times 10 to the 11th meters from it, that means that light has spread out over an area equal to a sphere of that radius, okay? So the intensity is going to be the power divided by 4 pi r squared, where this will be our r, okay? And this is a basic concept of astronomy, right? You've got some emitter of radiation. You've got, it's surrounded by this giant imaginary sphere, right? And we are 1.3 times 10 to the 11th meters from it, right? So that radiation is, by that point, will have spread out over that area, right? Okay, so 2.9288, etc., right? Times 10 to the 25th watts. And then that's divided by 4 pi, and then how far we were, 1.30 times 10 to the 11th meters squared, right? And this will end up being watts per square meter. So I'm going to take the number on my calculator, divide by left parenthesis 4 times pi times 1.3 times 10 to the 11th squared, right parenthesis. Okay, this should work. It's not very bright. 137.9 watts per square meter, right? By contrast, the sun, we're about that distant from it. The sun, and it's about 10 times that, but that's because the sun is 10 times as luminous as this star. All right. Basic astronomy lesson here, I guess.